All right, so let's look at this problem. We're trying to find the displacement at C, which is right there in the middle. Just the displacement, not the slope. Let's talk about the three methods that we've introduced so far. Let's talk about first direct integration. Could we do direct integration on this?
Yeah.
Of course, the answer is yes. What would we have to do? We would have to write two expressions.
Yeah.
Now, we would only be using the expression in the second half because we just want the displacement at C, but we still would have to solve for those constants there, and it could be a little challenging.
Yeah.
There's no real good boundary condition for slope, so you'd end up having to solve for your, in this case, 4 integration constants, probably simultaneously. Can do it, but probably that's not going to be a high choice. What about conjugate beam? I like that. This is a good conjugate beam problem. I'm guessing that the moment on the conjugate beam on the right side would just be triangular. And that wouldn't be too hard to manage. You could probably do that. So I think that's more of a priority. I have to rank the now conjugate beam direct integration. Let's see how we could do this with virtual work. And then we can kind of compare and contrast. So the first thing we have to do for virtual work is, well, we have to find moment expressions for this, right? So can I write a single moment expression for the whole beam? No. I'm going to have to write one for the first 10 feet and a second one that's good from 10 to 40. In both those conditions, I'm going to need to know the reaction. So let's find those first. So here's the reaction at A and the reaction at B. And let's find those. So first I'll sum moments about, I'll just do A because it comes first in the alphabet. And summing moments about A, the applied force creates what kind of moment? Positive or negative? Negative. So that would be minus 16 kips. And that's at a moment arm of 10 feet. And then my reaction at B creates what kind of moment about A? Positive. And that has a moment arm of 40 feet. So it looks like the reaction at A is 4. 4 kips. And then we can quickly come back.
What's the reaction at B?
What did I say? It should be B. I'm sorry. Thank you. I wrote A there too. I had A on the brain. Sorry.
It should be D.
I'm summing moments about A.
But you're all the way at D.
What?
You're at a point B more. You're at the end of the B. A, B, C, D.
Oh, it has. Oh, I'm seeing. I'm just making stuff up as I go along. All right, I see what you're saying now. Let's go back and call that D, which is my prospective grade on this problem. That's ugly. I think you get the idea. Let's see if I can straighten this out next. So we'll sum forces in the y direction. Make sure it's equal to 0. So I've got my reaction at A up, and let's see, my reaction at D is up. And my force 16 is down. So it looks like my reaction at A is 12. Okay? Did I get that right? That seems reasonable. Since your load is shifted to the left, you'd expect the left reaction to be higher. All right, so now I got to find my moment. So to find the real moment, I'm going to have to break this thing up into 2 pieces. So I'm going to cut it here, somewhere between A and B. Do you want to work the left side or the right side? I think the left side is a good choice. So for a value of x between 0 and 10, here is the left side of the beam. The reaction at A is 12. I have my distance x, And then I have the moment M. So solve for the moment. That's not so bad. I'll just sum moments about the cut. Make sure it's equal to 0. What I have is the internal moment, M, which creates positive moment. And then I have 12, which is creating negative moment, times the distance of x. So it looks like the real moment is equal to 12x. And that would have units of kip feet. Now, can I check that? Do I know the moment somewhere between A and B?
A.
Yeah, what is the value at A?
0.
0, and you can see my equation predicts that. Now, when I get my second equation that's going to be good from B to D, I will check that joint point that they have, that common point, make sure that that's... So let's go ahead and do that. So what is going to be the moment between 10 and 40 feet? Well, I'm going to cut it somewhere here, left side or right side. I think I'm going to go right. So that right-hand reaction at D was 4 kips. And of course, we're measuring from the left up to the cut X. And that means the remaining segment that I have here is going to be 40 minus X. And then I'll be looking at the internal moment there. So all I have to do to find that moment is, again, sum moments at the cut. We've done this a few times. You should be getting good at it by now. So the moment with right-hand rule, this is a negative moment. And then about the cut, this 4 kips creates a positive moment. And that will have a moment arm of 40 minus X. So we should get a moment equal to... I'll go ahead and run the 40 through. It'll be 160 minus 4x. And that will have the units of, again, it's a real moment, so it'll be kip feet. Now, do we know the moment somewhere in this range from B to D? Yeah, we know the moment at D it is 0. That would be at x equal 40, so you put in x equal 40 here, you get 0. What about the point they share at 10? So if I plug in 10 here, what do I get? 120. If I plug in 10 here, I get 120. So I'm pretty comfortable that those moment equations are okay. All right, so now let's do the virtual beam. So what does my virtual beam look like? Well, it looks like this. I'm still going to have a pin and a roller, so I'll have reactions. That will be RA. Let's see if I can get this right now. RD. And now we have to make a choice. The problem says, well, not really have to make a choice. We just have to apply the problem of the technique. We want the displacement at C, which is right here. That's the midpoint. So what do I put at C? My virtual load. And I'm going to assume that it acts down. I think under this load, I expect my beam to have negative displacements everywhere, all down. So I'm just going to go ahead and put my virtual load there. And it has right in the middle. So that's 20 and 20. So I'm going to have to now compute virtual moments. Can I write a single virtual moment expression for the whole structure? No. So I'm going to have one from 0 to 20, and a second one from 20 to 20 to 40. So I'm going to have to find my reaction. So I'm going to squeeze that in right here. So again, I'm going to sum moments at A. And about A, this virtual load creates what kind of moment? Negative. So it'll be -1 times A with a moment arm of 20. Excuse me. And then my RD reaction creates what kind of moment about A? Positive. times 40. So it looks like RD is going to be 1/2. And you probably can do this in your head, but I'm going to go ahead and write it down. If I did sum forces in the y direction, I would have RA acting up, RD acting up, my applied virtual load down, so I would get a reaction for A that is also 1/2. And that should not be too surprising. Now it's time to write some moment equations. So let's write one that's good from 0 to 20. I forgot to underline these to emphasize the range, so I'll go back and just do those. So we're going to go from 0 to 20, so I'll make a cut here. Left side or right side?
Left side.
Left side I think is a decent choice, so I will do that. I will put on my reaction that I found at A, which was 1/2, and I will assume my positive bending moment. I'm using the lowercase value for M there to indicate that's a virtual, and then that at some distance x. So I can now sum moments at the cut, make sure it's equal to 0. And what do I have? I have my virtual moment M. About the cut, I have a negative moment created by the reaction, 1/2 x. So it looks like my virtual load is just x over 2. And then I'll have to do it again. Find my virtual moment from 20 to 40. So I'm going to cut the structure here. Left side or right side?
Right side.
Yeah, I think the right side looks pretty simple, so I'll do that. So here's my right side. On that right edge at D, I will have a reaction of 1/2. Measured from the left to the cut, that distance is x. So the little segment of my free body diagram would be the total length minus x, which is 40 minus x. And then interior, I'm only worried about the moment right now. So there's my virtual moment. So we'll do the same thing. We will sum moments about the cut. Make sure it's in equilibrium. So when I do that, starting with the moment, is that a positive or negative moment with my sign convention?
Negative.
Negative. And about the cut, the 1/2 creates positive moment. So there's the force 1/2. The moment arm is 40 minus x. So it looks like the virtual moment is 1/2 40 minus x. Can I check those?
Yes.
Yeah, do you know anything about the moment in this virtual beam?
It should be 0, 0, 0, 0.
0 here and 0 there. So on the left side, I've used this equation. So you plug in x equals 0, hey, it works. On the right edge, I have to use this equation. Plug in x equals 40.
And it works.
That works. And now the point they match at 20, you plug in 20 here, you get 10. You plug in 20 here, you get 10. So all seems well. The only problem is I've run out of paper.
Oh, I got you.
So you got me? Oh, you were ready.
I was ready. I knew you were ready.
Very
Good.
Smells fresh. So now going back to the problem, what are we going to do? Remember the original definition was we're going to integrate over the length the real moment times the virtual moment divided by EI. Right? Can we integrate the full length, 0 to 40? No. Well, first let's look at the real moments. We've got one that goes from 0 to 10, and then this one from 10 to 40. So we're going to have to at least go 0 to 10, and then 10 to 40. But what happens down here? Well, this one's good for the first 10, but then it goes from 20. So I'm going to have to match 10 to 20 with this one, with the first one. And then from 20 to 40, this one's good, and this is also good from 20 to 40. So it's going to be broken up into 3 segments.
This is the part where you assume that we're good, right?
You're going to have one from 0 to 10. I'm just going to do it shorthand. And then one from 10 to 20. And then a third from 20 to 40. I think you can see that although this is not hard, it is incredibly tedious. And that maybe I should have used conjugate beam after all for this problem.
Yeah.
But we're still going to do it because that's what we do. So, they all have a common EI in front of them. So I'm going to factor that out. Just let it sit out here on the front. So I'm going to do the first one. So the integral from 0 to 10. So there's the real moment from 0 to 10, 12x. And the matching virtual moment from 0 to 10 is x over 2. The next integral in the sequence is from 10 to 20. What's the real moment from 10 to 20? It's this one. 160 minus 4x. What's the virtual moment from 0 to 20? I mean, from 10 to 20. It's still this one, x over 2. And then the final piece, from 20 to 40. What's the real moment from 20 to 40? This one. What's the virtual moment from 20 to 40? I'll slide over so you can see it. There it is. 1/2 40 minus x. And I still got a lot of work to do. So I'm going to stop here because if I gave you this problem and you chose this method, which may not be a good choice, you would stop here too, probably. Not only do we have one of these multiple limit integrals, we got 2. This would be a lot of calculation, and I don't really think that's important on the exam. Now on homework, I don't care. You got all day. So what I'll do is I'll go back to my office and I'll finish this problem up. I'll actually do the integration and do the evaluation and show you the numerical value. But I'm also going to draw a big red line here indicating that this is all I need to see for the virtual work equation. In fact, I left off a piece here. This should have been the displacement at C is equal to that. Okay?
This method is fundamentally a lot easier than the other methods. It just takes
I think conceptually it'll work for just about anything, anytime. But in application, it can be quite tedious. This is not hard. It's just a lot of mind-numbing cranking the wheel. And you don't have a lot of time to do that on the exam. So I think if you can get to this point, you've shown me that you understand the concept. And if I gave you another 20 minutes, in a comfortable place to sit, you could probably do it. Ooh. All right. Any other questions?